hi everyone. As our major task in our subject real analysis, our group Faultis 5 was able to come up collaboratively with a video presentation about the Lebesgue Measure. Now, J.R.R. Tolkien, author of the famous Lord of the Rings, quoted Gandalf saying, "A wizard is never late nor is he early, but he arrives precisely when he means to." We hope that as math wizards, we can be able to digest what we will be learning in the entire presentation. Now, in this case, just like we can measure how much we have of an everyday object in different ways, for example, the mass, the volume, the length, and etc., we can measure how much set we have in many different ways also. So for that, stay tuned, stay connected as we begin this presentation. Once again, this is Philip Jason Falsis, and I am tasked to present the important terms related to the Lebesgue measure and the definition of a measurable set. Now, we have the following important terms, or these terms are essential in our study or our discussion about the Lebesgue measure. We have the interval. We also have the length of an interval, followed by the countably additive measure. We also have the translation invariant, followed by the monotonicity. Then we have the countable sub-additivity, the counting measure, the sigma algebra, and of course, the very important one, the outer measure, symbolized by M and an asterisk symbol. Now, what is the definition of a measurable set? It says here that a set E is said to be measurable if for each set A, we have the outer measure of A, which is equal to the outer measure of A intersection E plus the outer measure of A and the complement of E. Now, this is further illustrated in this figure that we have. Given that set E and set A exist, the measure of set A, or the measure of A, is determined by the intersection of two sets, and the outer part, set A, intersected by the complement of set E, based on this illustration that we have. Therefore, if the measure of E now is equal to 0, we can take note that E therefore is measurable. If the measure of outer E is 0, again, E is measurable. So in this present case, the outer measure is Lebesgue outer measure, and we can say that E is Lebesgue measurable for this example.
Good day, everyone. This is Portia J. Starke, and I am tasked to define the Lebesgue measure and some of its properties and theorems. Henry Leon Lebesgue lived his life from June 28, 1875 to July 26, 1941. He was a French mathematician known for his theory of integration, which was a generalization of the 17th century concept of integration, summing the area between an axis and the curve of a function defined for that axis. His theory was published originally in his dissertation, Integral Length Area, at the University of Nancy during 1902. The Lebesgue measures are the standard way of assigning a measure to subsets of n-dimensional Euclidean space. For n equals 1, 2, or 3, It coincides with the standard measure of length, area, and volume. In general, it is called n-dimensional volume, n-volume, or simply volume. It is used throughout the analysis, in particular to define Lebesgue integration. Sets that can be assigned a Lebesgue measure are called Lebesgue measurable. The measure of the Lebesgue measurable set A is here denoted by lambda of A or M of A. The Lebesgue measure on Rn has the following properties. Number 1, if A is a Cartesian product of intervals I sub 1 by I sub 2 by I until I sub n, then A is Lebesgue measurable and lambda of A is equal to the product of the intervals. Hence, the Cartesian product denotes the length of the interval I. Number 2, if A is a disjoint union of countable many disjoint Lebesgue measurable sets, then A is itself Lebesgue measurable, and lambda of A is equal to the sum or finite series of the measures of the involved measurable sets. Number 3, if A is Lebesgue measurable, then so its complement. Number 4, lambda of A is greater or equal to 0 for every Lebesgue measurable set A. Number 5, if A and B are Lebesgue measurable and A is a subset of B, then lambda of A is less than or equal to lambda of B, a sequence of number 2, 3, and 4 properties. Number 6, countable unions and intersections of Lebesgue measurable sets are Lebesgue measurable. It is not a consequence of 2 and 3 because a family of sets that is closed under complements and disjoint countable unions does not need to be closed under countable unions. Number 7, if A is an open or closed subset of Rn, or even Borel set, then A is a Lebesgue measurable. Number 8 property, if A is a Lebesgue measurable set, then it is approximately open and approximately closed in the sense of Lebesgue. Number 9, a Lebesgue measurable set can be squeezed between a containing open set and a containing closed set. This property has been used as an alternative definition of Lebesgue measurability. More precisely, E is a subset of R is Lebesgue measurable if and only if for every epsilon less than 0 there exists an open set G and a closed set F such that F is a subset of E, which is a subset of G, and the lambda of G in F is less than epsilon. Number 10 property, a Lebesgue measurable set can be squeezed between a containing G delta set and a contained F sigma. If A is a Lebesgue measurable, then there exists G delta set G and F sigma of F such that G is a subset or in A and A in F. And the lambda of G and A is equal to the lambda of A in F, which is equal to 0. Number 11 property. Lebesgue measure is both locally finite and inner regular, and so it is a radon measure. Number 12. Lebesgue measure is strictly positive or non-empty open sets, and so its support is the whole of Rn. And the last property here, if A is a Lebesgue measurable set with lambda A, which is 0, a null set, then every subset of A is also a null set. A fortiori, every subset of A is measurable.
Hi everyone, this is Lebeg Danes, a student in PhD in SciEd, and I am to present how important Lebeg measure is. This Lebeg measure is significant in understanding its subsequent topic, which is the Lebeg integral. This Lebeg measure, which is the prerequisite of Lebeg integral, is needed in dealing with partial differential equations, that is, when the derivatives are weak. Many of the times, the mathematicians make use of the knowledge gained in solving Lebesgue integrals by solving the partial differential equations when the derivatives are weak. Two steps are necessarily involved that shows a weak solution exists while the proving of the presence of regularity result is done. Another case is in solving the Fourier transformations. The presence of the various numbers of the results on the convergence of the Fourier transformations invites the knowledge of the Lebesgue on proving them. Lebesgue measure and integration put the Fourier transformations on the solid, thus easing out a way to solve the problems. Another application that involves the use of the Lebesgue is on probability. The modern view of probability applies to measure theory. The probability space is easily understood since one can make the sense that things said are real. Lebesgue measure is necessary for mathematics as one is allowed to deal the functions in an excellent and elegant way. In mathematics, things such as the function space are easily solvable since there is a rigorous foundation. In most mathematical physics, the Lebesgue integration and measure theory form foundations to solve the physics-related equations.
Hello, I am Herbert Rex Capalla, a PhD student at West Visayas State University, and I will be the fourth presenter. My discussion will be on a recent published article on Lebesgue measure that will provide a brief explanation on how the article illuminates our understanding of real analysis. The article is entitled The Lebesgue Integral and Measure Theory by Sarah Al-Johani. This article shows the aspect of the Lebesgue integral and the measure theory where the mathematical knowledge can be applied, how to do it, and what led to the discovery of the Lebesgue integration. The limitation of applying the theory will also be discussed. Understanding the field of mathematics would require the wholesome interest in doing calculations and solving the problems that may be difficult to solve using other methods. Excerpts from the article about Lebesgue measure includes the following: that Lebesgue measure originated from one of the French mathematicians named Henri Lebesgue, who made it possible to have a common standard way that involves the assigning of the measures to the subsets that have n-dimensional. The measure theorem provides an analysis of the length, area, and volumes of the Euclidean spaces. The notion of the measurements are generalized in this field and the practical answers are thus made easy to solve. The measure is taken as any function that is defined on any given subsets that tend to satisfy the given list of properties. Measure theory is thus one of the branches of the real analysis. The theory is useful when investigating the measurable functions and integrals of the given functions. As a characteristic of the Lebesgue measure, the use of the outer measures make it easy to translate the values in the given exotic functions. The subsets of the real numbers are taken as the conditions when solving the functions. Through the mathematical knowledge, the existence of the given sets that do not meet the Lebesgue measure conditions provide a consequence of a set of certain set theoretical axioms. These can be interpreted to be independent of given number of the conventional systems that relate to the axioms of the set theory.
Good day, everyone. I am Mary Feduno, your last presenter, and I will be presenting Lebesgue measure using analogy and the way we can use concept and theorems to live life in the fullest. In reality, no matter how hard life is, whatever the circumstances are, your identity will never change. You are not shaped or sized by circumstance. You just learn to go with the flow and be yourself. Many bits of knowledge only come through experience. Think of ourselves as being like a biscuit mold. It's only by pressing ourselves against the dough of life that we get to see what shape we actually are. Even though there always be a lot of people similar to you, there can only be one you. Be yourself no matter what. Some will adore you and some will hate everything about you. But who cares? It's your life. Make the most out of it.